welcome to part 2 of my Intro to PCB Design video. So this was a lecture at Dalhousie. If you didn't see part 1 or you skipped it because it was too long, in this part we're going to look at how you actually order the boards and look at the pricing of them. Part 3 we'll do the design, and then part 4 we're going to build them up. So how are boards actually made? This, I had a little diagram of this before, but basically it's all this etching stuff. So we have copper. Resist gets added on top of the copper, and then it etches away. And what you end up with, and I actually drew this backwards in my part 1, but I'm not going to go back. Too bad. You end up with this problem that basically you have this under etch, right? So under the resist, etching happens here, so the trace widths get too narrow. And so we have this problem that we end up with, whatever our design traces is, they can be a tiny bit narrower than we meant them to be. So obviously, if this width, this goes back to our trace space, is really small, it becomes more, it's easier for these to under etch further, and so it's more likely we're going to have opens in our traces. So this is why smaller traces get more and more expensive. To make sure you didn't accidentally make a trace too small, we run something called design rule checks, which basically say, hey, here are what I designed my board for. And this is all part of design for manufacturability, DFM, right? Which would also encompass things like choosing the right footprints that match your soldering process and stuff like that. But for PCB design, most of the time when people are talking about DFM, for really simple boards, what we mean is that the boards get made correctly. If you're doing even, small amounts of assembly, automated assembly, you also want to look at how do you increase the yield or likelihood that you're going to have successful boards after the PCBs are assembled into PCBAs. But running DRC is really critical, right? Failing to do this, it could just be the fab will email you and say, whoa, what's going on with this board? Or it could be your board's totally wrong. I think one of my worst cases was I forgot to, so basically it was a pretty complex FPGA board, so 8 layers or something like that, and I had at the last second moved a couple vias around and forgot to re-pour a ground plane, something that would be caught by DRC, and the board I got back basically had shorts. You couldn't use it. It was shorted at hundreds of locations, straight to ground. So if you don't do it, bad things happen like that. Anyway, so when you have your design files, you're going to use something called Gerber's, so most of the time we're using something called Gerber's and NC-Drill. You're not always going to be using this, but this is how we communicate our intent to the fab itself. There are more recent ones. So in industry, they're more likely to use file formats that have more control. Basically what we'll see is these ones are a little bit ad hoc, and it's really because they have come from such a long history of the design. But they're by far the most popular, especially for little prototypes and things like that. You're just going to use Gerber's and NC-Drill files. The other thing you might be asked to share is a net list. So most of the time this is going to get extracted automatically. They'll take your files and figure out what the connection should be. So boards, you should get boards have an e-test done, or electrical test. What the e-test does is it uses a bunch of probes to check that you don't have opens due to this. So they're literally checking the resistance of all the nets on the board is correct, and you don't have any opens. There's some additional cost to this sometimes, or they may roll it in. There's always an additional cost, whether or not they expose it to you. But the thing is, if you don't do this, you could build up a board, and the board has a error from the manufacturing, not from the design, right? And that can be really hard to troubleshoot if you have a new design that you don't know if it works or not. So it's something I encourage you to do. The cost is pretty minimal normally, unless there's a really simple board that you can look at it. But once you get to multiple layers, it's always worth doing e-tests. Gerber files are old, so from the 60s. The terminology basically reflects how the PCBs were actually made back in the day, right? And what you had is you had a film that was exposed, right? So some of this is similar, but the way it's exposed to the film is different now. But what you had is you had a film here you had optics, and the goal was to draw on this film your PCB pattern, right? And to do that, you basically had different patterns, and these were the apertures that you could draw. So, you could have round, you could have different shapes for different traces or like pads or stuff like that. So your file defined what aperture to use, and then it would define, okay, now drag that around on this film to expose it. So you used to have even more variation in Gerber files. This file would be separate because it had to tell them what apertures are loaded. Now it all gets kind of rolled into one, but you will occasionally see references to a separate aperture file, and within the Gerber file, if you look at it, it will have reference to apertures, which is basically what pattern gets moved around on the board to draw your traces. Yes, that's what I said. The other file is the numeric controller NC-Drill. Sometimes it's called Exelon, so Exelon was a brand name, or have other names, but this has the drills for the vias and holes on your board. It sometimes is split into as well if you have slots, so with a lot of connectors, you may have a separate file that includes slotted files, so you may end up with two NC-Drill files. And you also may have files if they're not plated through holes. So if you remember when we talked about, most of the time we drill a hole and then you plate it through. Depending on, you may have holes that you don't want plated through. So if you're mounting things in them, if you don't have electrical pads on the top and bottom, you could end up with separate holes that are not plated through holes. So those will get separated just so that the manufacturer knows what's supposed to be plated through and not. So things are pretty good now for automatically picking it up, but there's a lot of parameters in the file that you sometimes have to specify for the fab. Normally, the two things that are important is if it's millimeter or inch. And again, they're pretty good at picking up because PCBs, if you get this off, it's so much larger that it's pretty easy to just figure out if it's a millimeter or inch file. You also may have to specify precision. So there's different ways of representing how the decimal place is encoded, how many numbers you had before and after that. So it's become relatively standard for most design software. Most of the time you can just accept the defaults, but if you run into issues, you may have to go dig into that. The other thing that's common to include is a README file. So this is just a simple text file that has here's the board parameters, the size of the board is nice to show, what files you've included, and maybe your contact information if they have questions. Avoid over specifying things. So when we look at the ordering process, we're going to use their website to specify, we had the different PCB colors, so we're going to specify all that stuff through the ordering process. We can also specify it in the README file, but try to just put it in one spot. Or, if you always want, this board was always supposed to be red, so I'll put it in the README file in case I select the wrong option or someone orders the wrong one. Hopefully they check the README file and say, this board was supposed to be produced red, maybe they selected the wrong one, let's stop and check. So here's a very minimal README file, right? And so I have, and again, just a text file. It's 2-layer PCB. So if they see more than 2 layers there, it's a problem. Normally this would be if it's an 8-layer PCB and they're designing it or manufacturing it to be 6 layers, they might say, wait, did a couple of the layers get dropped? Or did they tell us the wrong stuff when they were quoting this? I've got the size of the board in there, the individual PCB size. Here's an example, right? So I have a finish. I'll accept 2 different finishes here because, whatever I was ordering, sometime I might have done hot air surface level, sometime I might have done ENIG for a prototype run or whatever it was. So I actually just have both written in there because I don't really care. When I was going to production, I might change this to specify the final version I want. And in this case, I want a blue solder mask, so I'm going to specify that in case it gets dropped. Here, so you notice I don't even have the underline file names. I just have the extension because this is kind of like a copy-paste thing I'll often use here. So we have the different layers. So we have the top silkscreen, the solder mask, the copper layers, the bottom solder mask, the bottom silkscreen, and then there's an outline layer that defines the board outline. Most of the time Fabs prefer it as a separate file, and this can vary, but this just defines how they're going to route the board out to cut it out of the panel. And as mentioned, my drill file, so in my case I call them .NC-Drill. You may have different file names. This was Altium-ish defaults. I changed a few of them. From KiCad, we're going to see different file names. Doesn't matter. There's no standard here, so I use .gbl and GTL and stuff like that. Sometimes you'll just use .gbr. Try to make them super descriptive about what layer is what. I also have, so we'll look at, and when we get into assembly stencils, so I have a paste layer used for stencil. In this case, it's a one layer or top layer only assembly, so there's no bottom assembly information needed. It exports by default, but it's just blank, so I just say it's not used. Here's a more detailed README file. And this is for 8 layers, right? And so I mention in here all the layers, including inner layers and plane layers. Remember, plane layers mean I have connection basically everywhere, so that whole layer is used as a plane layer, as one net, or maybe a few nets, but there's not a lot of traces on it. And inner layer, I'm just using for traces. So there's no difference in the actual construction of it. It's just a difference in the nomenclature. And in this case, there is a minor difference in the file that I'll show you in a second, because you'll notice it says inverted in all the plane layers. I have a mention about the layer count marked in the PCB file, so I tend to mark within the file what the layer is, like 1, 2, 3, 4, 5, 6, 7, 8, so that you can see when you're manufacturing it's being done correctly. I have a NC-Drill file, so there's 2 NC-Drill files. One's called a slot file, one is just your standard drills. And I also have a stack-up note. So when we talked about the stack-up, we didn't really go into this, but here I list what the stack-up was used. This board didn't have any controlled impedance or anything where the stack-up would really matter, so I also have a note that any 8-layer stack-up is okay. And this is almost more a note for me that here's what it was made for when I've made it the last few times. And finally, I say that it's e-tested. I can provide a net list. A lot of the time, their workflow just extracts it from the Gerber files too. The other thing up here is there's a design technology. So this is what the board's designed for. This should match what I order, but I just have it there so it also validates what they've expected. That inverted layer thing. So this is an inverted layer. This is a plane layer. And what it does is, because it's mostly copper, it just marks where there's no copper, right? So these are what are called thermal reliefs, but you can kind of see there's these patterns here where there's no copper connected. This drill here has a kind of lightish green around it, which is an excluded copper zone. These vias are connected. There's just a hole straight through the plane. It just automatically connects to this plane. It's easier to show an inverted layer. It keeps file sizes lower probably because you don't have to you just show where you're not having copper, but it helps visualizing. And again, back in the day, it would have been easier to process this as an inverted layer potentially. So that's kind of why we have this note in here. Most of the time they'll pick this up. It's pretty obvious, but I always like to specify if a layer is inverted or not, just to make sure there's no issues. The other thing that you're pretty unlikely to have for just simple prototypes, but very common in industry or professional designs, is a manufacturing drawing. So what this is this is just another Gerber file. It has an outline of the board. In this case, Altium helps me kind of include a photo of the board on it, or a render of all the layers. So you could see it here. But it has a whole bunch of notes. So it has a few things. It has drill markings. You may have a separate Gerber drill file that has this as well. In this case, I have some information about the drill sizes. And I have details about, here's the finish I need. Here's, this has a card edge. Here's the card edge. Dimensions, things like that. So this is pretty common to have in a design as well. So when we go to order, there's lots of different fabs you can use. This is going to change over time. So, I have these in here, but it may turn out that these are terrible. So you should look at whatever is the coolest, most recent. This is January 2025 I'm recording, so hopefully it's still accurate for a bit. In the US, Osh Park is probably some of the original maker-friendly service to people. Here in Canada, shipping's a bit slower, but it's still a really good service. It's very maker-friendly. They've always had a lot of great resources and tools, so it's something that is worth checking out. Overseas fabs are super popular right now. JLPCB is quite popular, very low cost. You can get quite high-end boards out of them too, though. PCB Way is also quite good. They have access to higher-end processes, so you can even get more complex boards done from them. Still quite still quite user-friendly, slightly less so than JLPCB, but this is, getting close to splitting hairs. As a note, so I have a note here, and this was, again, for people in my lecture. This is currently happening. There's a Chinese New Year or Spring Festival sort of thing. A lot of things shut down, shipping shuts down, so every year when if you're trying to do production right now, it's a huge hassle because other fabs everywhere get busy. So it's not just the case that, everyone's outsourcing to China. No, the big chunk of manufacturing's slowing down, so fabs everywhere get super busy, no matter where you are. In Europe, Euro circuits, so I don't use them as much just because the shipping to me is more, but they have a great website. It's really easy to see how changes in technology affect price. The prices are pretty good, speed's good. So if you're in Europe, that's good. There is some other European fabs actually, again, because of shipping. I don't use them as much, so it's worth checking out what all is available. For me, it's actually faster most of the time to use Chinese fabs than anything else. The shipping from there is almost the same speed. So just for pure getting boards back as soon as possible, for me, overseas fabs are actually the best choice, which maybe seems silly, but that's just the way it works. Let's look at quoting via JLPCB. So I have their website up. So in the slides, there's some examples. And we can quote, and it doesn't really matter what you click, because normally what you're going to do is you're going to upload your Gerber file, and it's going to automatically detect the outline and actually detect layers and a bunch of other stuff that are in it. But we can also just specify, if I was making a board, like a simple 2-layer board, 10 by 10 centimeters type thing. There's 5 boards, so we would specify normally PCB thickness 1.6 millimeter, leave that alone. You could specify the color, so green. One thing JLPCB does is they have some different churn times for different options. They run green faster, so different fabs will do this differently. If you want the fastest possible turn, just do green. I maybe want red, so it says it's going to take 2 more days. And in this case, it's actually going to happen after Chinese New Year. Normally, you wouldn't have that as well. You can pick the surface finish. So as talked about, a lot of the time, this is going to be lead-free hot air surface level. But ENIG can be popular, especially with BGAs. Just for reference on pricing, if I go up here, so they have some special offer of $2. The special process fee is either probably because I've chosen the red solder mask, right? And this changes all the time. So you can see choosing the red solder mask changed the pricing quite a bit because they had this crazy discount on right now. If I go to ENIG, it's not that much more. Right, so there's a $16.70 surface fee. And this is total for all the boards. So it's $35 for 5 boards, right? What you'll notice too is that if you go up, it doesn't substantially. So it's $55 for 20. And this generally is the case that if you're only getting a few boards, you're paying a lot of money per board compared to getting more and more. So if you're doing a project where you're doing a makerspace and you think other people might want to build them, it's worth getting more boards, as long as they're not going to be waste. Obviously, don't just do it for no reason, but it is worth checking that out. The rest of the stuff you generally don't need to worry about. So the via covering thing here, this is going to be specified via the Gerber file. So this is kind of an artifact if you're not specifying in the Gerber file. We talked about via in pad, which is this epoxy filled and capped. So this automatically happens if it's 6+ layers. So I couldn't remember when I was looking, talking in the lecture, but you can see that you're automatically getting vias that you could do via in pad if you wanted beyond 6 layers. Minimum hole, again, this is all going to depend on what your design parameters are. So yeah, so that's it. So it's pretty easy to order. You just say save to cart and you'd be done. The generic ordering, as I mentioned, I'm sometimes, if I know for sure that I might be changing the solder mask color, sometimes I would order green for a first board and then change it for my next run. I might just, in the README file, specify a solder mask as star to say, I don't care, go with what I ordered. The other thing you do with JLPCB is you can order full assembly. So there's a few places that have done this, Macrofab I know, and a few others in the US, but JLPCB has a pretty nice web interface that makes it really easy to order full assemblies. You can do this from other places, PCBWay and a bunch of them, and it's pretty easy. You send the same information I'm going to show you here. I'm going to use the JLPCB one because it has a little web interface that I can show you. You'll need a couple more things for this. So we need a bill of materials file. The best way to do this, so this is a list of all the parts and part numbers that are on your board. It can be something you just maintain separately, but when we look at the design process, we're going to actually include part numbers in the schematic symbols, and that way we don't risk forgetting that we made a change or anything like that. There's just one source of all the information we need. Generally, they look something like this. So for JLPCB, you're going to have to download an example one and then format yours to look their way, but you have, here's how many parts I have, here's their designators. Here's sort of, I have a short description. It's 100 nanofarad 402 cap, but that doesn't specify everything about it. Voltages, all that. So I also have a manufacturer part number, which in part 3 we'll look at, how you pick these parts. What you're also doing is you need to specify data for a pick and place machine. So this is a small little desktop pick and place we're using for small runs and things like that. And so you can see it's just picking up each part, right, and placing it down on the board. So what we need to do is we need to tell this machine where each part goes. A bigger production line would look something like this, right? And so this was from Z-Axis Inc. You can check out the link if you want to get an idea of what's included. But, this is a more normal size production line. So you have these very big machines that would be running your boards. So this pick and place file or component placement location file has basically a few things in it, and the format will vary a lot per what your fab wants. Sometimes fabs don't want, I've had it before where they say don't give us any information about what the part is. We just want the designator because they don't want conflicting information. Most of the time they'll just ignore it. But, again, you can check for what each fab. The important thing is it has the location of the part and the designator. So it says this part is placed at this location. It also has a rotation in it. That rotation is what angle the part is placed at. Little caveat here is that how this is defined may not be super useful because most of these parts are going to come from what's called tape and reel. So it's going to look like these reels here of all the parts in it. So you can have a reel of 5,000, 10,000 resistors, a reel of hundreds of components, and the pick and place machine picks them out of this little cavity here. So the rotation is relative to that reel. It'll be specified in the datasheet, so you'll have to go look at the datasheet if you want your file to be accurate. Most of the time your manufacturer just doesn't trust it. They're going to go through and look for things like resistors. It should be accurate. Don't mess that up or they'll hate you. Because these are easy. They're always the same way. Worst case, I guess they'd rotate all your resistors and capacitors, but the actual where pin 1 is located is much less standard somewhat standard, but in reality, they're not going to trust you. They're always going to check that. With LEDs or diodes, it's super important. It might not be obvious if the part is backward. You often have to tell them, here's what I'm using to indicate pin 1. Some workflows you let you do this. Even with JLPCB, they actually verify. So they say right on the website, ignore pin 1. We're going to go manually look at that. We can do a little demo here. So they have this demo thing where what it's going to do is it has a... So if you click that link that's in my description, hopefully this works. Give it a second. Come on, buddy. So it has a demo board. Okay, there we go. So it has this demo board, which just has JLC SMT. And so you can look at what the interface looks like without actually uploading any files. So this is just the board, no parts on it. What we want to do is we want to mount a whole bunch of parts. So JLPCB, they use LCSC. There's they can get parts from DigiKey Mouser, but there's also overseas suppliers that provide equivalent parts that you'll want to map a lot of your part numbers to. So normally what's going to happen is it's going to try to match parts. In this case, the BOM included their own part numbers, so the matches are really good. Go through and check the matches because I find the search isn't the best. And it's going to tell you, hey, we're missing parts. We need more parts for this one. They didn't have enough. Whatever the part number was at the time changed. So now we're going to replace that part. By default, it may need to do all of them. In this case, what's happened is it already had these in here. But their search, they have some 560 plus minus 1. We want a 402, so this is a 560 402. So if you search like 560 402, what you might want to do first is say in stock and potentially basic parts only. So they have an extended part library, which has more limitations. These are parts they can get from DigiKey Mouser or may have from them. Basic parts are ones that they've got tons of stock of. So I tend to, if it's just like resistors and capacitors, you prefer to do that. But, whatever. If you need extended, no big deal. What you'll see is that, it's come up with all sorts of, I just searched 560, not resistor, but it's come up with all sorts of totally unrelated things. I might uncheck basic parts, and we see a couple resistors. Let's see, are these 560 ohms? So this is 56 ohms. So this is where I say the search, it's matching parts of the part number is what's happened. So the part number part we want is 56 with 10 or 561. But what I might search is 560R, which is often used for in place of ohms. And the second one here, let's see, is a 560 ohm 402 resistor. It says they have lots of stock. So let's just hit select. And for some reason the demo project seems to not work, so I'm kind of going to ignore this. I don't think any of these are going to work. So this is 560 ohms. Yeah, internal server error. So there's something weird with the demo project. So the other thing you could do, let's say you didn't even find it, right? Is what's going to happen is it's going to say, hey, you have some that you don't have a solution for, just don't place them, which is fine. We can solder them on later. So if you get 90% of your board made, then that's pretty good. Then it's going to show you what the board looks like, right? So it's going to show the missing. We've got a parts that are do not populate. In this case, these resistors that I didn't have. So you can see those do not populate boards, and we can highlight the different parts here. So that's a pretty nice way to do our design. So you can also rotate. So you can see I can rotate parts and things like that. So if things are off, hopefully we can adjust this to get a corrected model, right? And because it's the demo one, I'm not sure why, but I think the demo one doesn't fully work here. But it should give us a quote for doing this, and then we could place the order. Back to the slides here. So I talked about LCSC, talked about finding replacement parts. Talked about this, so the suffix, if you haven't come across this is really common on schematics and stuff like that. I use this in the search, right? 560R is 560 ohm, 560K would be 560 kilo ohms, but we also use this in a replacement as a decimal place, so 5K6 is 5.6K. So at a glance, the reason we do this is it's easier to drop this by accident if you're just typing something in quickly. Typing 5K6, it's a little, it's a little more obvious when you look at a schematic or page, if you're zoomed out, that it's supposed to be 5.6K. So I use that notation a lot. Not everyone does. Same thing with capacitors and stuff like that, but you may run across this. So the silkscreen markings, so I mentioned that rotation, so I will also say that the silkscreen markings are going to be used to confirm polarity. So always make sure you're marking like pin 1 on your silkscreen if you're getting it assembled, or even if you're assembling it yourself. You're going to hate yourself if you've got to go back and look at every part for what's supposed to be pin 1. When the part's mounted, we should have pin 1 visible. The anode cathode marking, right, this can be a bit more vague, so I use these polygon type things for my LEDs, and then somewhere else document which is the anode or cathode. For JLPCB, they prefer if you just put a plus right on the board. I mean, most people prefer that. It's very obvious what is the anode or cathode with an LED or diode, or you could have a diode symbol is very common, so we have a diode symbol marked on the board as well. So just always mention what you're doing, because it will vary. Some people will mark the cathode, some people will mark the anode. Another sidebar, there's lots of sidebars on this thing. The TQFP in particular packages, but other packages will have this. There's a pin 1 marking, which is this little dot. There's IC ejector marks, so these are from the die molding process. These are not pin markings. So in this case, it's kind of obvious because you have these round circles and they're on opposite corners, and then there should be a more obvious pin 1. As another example, here's an ST tends to have packages like this where the pin 1 marking is actually opposite a die ejector mark. So this is a bit tricky. It's hard to see here, but this one has a more rounded, deeper sort of finish to it. This is a very flat finish. So when you're looking at parts, identifying pin 1 can be important. Check the data sheet. There may be other features. I don't think there is in this part, but don't always assume what's pin 1 or what's cathode or what's anode, because it does vary. LEDs and diodes are bad for this. On the back side of the package, sometimes they mark cathode, sometimes they mark anode. It does vary a bit. So always check, don't assume. But yeah, that's basically what I wanted to talk about with the ordering process. Some of this got into assembly a bit, I know. We're going to talk more about assembly in part 4. But the next part is going to be looking at designing a PCB with KiCad. So we're going to go through very quickly, super basic board. And then there's actually going to be another one that talks a little more in detail at the design for an inductive driver. But hope you enjoyed this, and I will see you in the next part.